I'm going to present to you this idea, the concept of integrating support for NVMe over TCP on the desktop from user perspective using GVFS, libNVMe, and udisks. It's all about this RFE. I'm going to go lightning fast through the slides, so please refer to that RFE for the technical details. Just for the introduction from user perspective, what is NVMe? You mostly likely have SSD drive in your computer. It just works, right? You have a block device, you just store data. You don't need to manage it anyhow. But there's more behind that, and the block device you are using is actually a namespace. Consumer SSDs typically have just one fixed namespace. The namespace is provided by a controller, and the controller is connected to a transport. In your local drive, it's a PCI Express transport, but there's more. And this is all wrapped in an envelope called subsystem, which has an ID, subsystem NQN. Think of it just as an identifier. You will see later. Okay, enter NVMe over Fabrics. It's a part of NVM Express specification and built on top of what I just said. Just some terms. Initiator is a client usually. Target is a server. I will be using these terms in the next slides. And Fabric, it's a transport medium. Different topology. It's not like just an IP network, but a fiber channel, a mesh, or whatever else. The work here presented will be transport agnostic. Yeah. So subsystem NQN is mostly used in Fabrics. That's just one of these primary identifiers. So the targets and why we are doing this work is that NVMe over TCP slowly gets adoption on the market, and even your home NAS box might offer you to share your data through NVMe over TCP along with other protocols like iSCSI. Actually, NVMe over TCP aspires to replace iSCSI in the long term, hopefully. But we'll see. Another possibility is cloud storage. Once you rent a space somewhere, they can export the block device over NVMe over TCP over the internet. Enterprise storage arrays, it's been in place for some years already. And in your home network, you can also configure a software NVMe target in a Linux kernel. Essentially, you don't need any external dependencies because this is built in kernel. It's very similar to LIO target for iSCSI. And you can configure it through config.fs, just creating a structure of symlinks and directories. Or you can use NVMe CLI, which is very similar to target CLI with user-friendly shell with a structure. It consumes JSON, a very, very simple JSON, and it just defines what block devices are you going to export, and ACLs, hosts, binding network ports, network interfaces, and so on. Initiator as a client, that's very interesting and very simple as well. Also, you don't need any dependencies if you are on embedded system, for example. You can just write a specially crafted string to dev NVMe fabrics, and it will just appear on the system if it connects. For our purpose, we are mostly using NVMe CLI, which is built around libNVMe. libNVMe is essentially a translation of NVMe Express specification into C headers. It's a really small C library and basically provides a complete functionality, up-to-date specifications. This is an example of a simple connect command, just 3 arguments. Of course, there are more, but these are just like fine-tuning for timeouts, retry, resilience, and this kind of stuff. The string down there is the subsystem NQN, which has some syntax, some form, doesn't matter. NVMe discovery. It's another well-supported service. It's just allows you to list exported subsystems on the target. Again, example using NVMe CLI, very simple. Okay, GVFS. That's the project we are trying to integrate the work into. It's an extension point to glibgio, and it's been well adopted by desktops. You don't need to run desktop session to use GVFS. You can just run a debug session locally. It's a non-visual stuff, but allows you to access variety of resources. GVFS has backends. These are protocol implementations, mostly. It also has volume monitors, which manages instances of volumes, bulk devices, and mounts. GVFS uses URI as a primary identifier, very similar to URL. We also have HTTP backend, which just consumes whatever you pass to it. So protocol part, optional authentication, host name, and path to the resource. You can basically identify almost anything. Just an example, this is a file browser in GNOME. Notice the URI in the right top corner. I'm accessing my home machine through SFTP. And it's also integrated, for example, in GTK file chooser. It will show up as a folder and can just open file from anywhere. This is a list of non-exhaustive list of backends. Most commonly used for you will probably SFTP and Samba browser. And this is the part of the proposal itself. So NVMe specification specifies NVMe URI to some form. It's only part of NVMe Express boot specification for the moment, but we are trying to make it more general. And the URI is slightly different because it needs to accommodate the transport. So you see the examples, NVMe plus TCP. It's how you can specify transport. Like NVMe plus FC will be another way through fiber channel. So there are 3 parts. You have a host name, and you have subsystem NQN, and an optional namespace ID. Not relevant to this case for the moment. This is the proposal of a new GVFS backend. So I didn't mention that there is also a mechanism to discover discovery controllers on the network using MDNS. GVFS already provides a network backend which uses Avahi to discover services on your local network. This is typically used for Samba servers, just like on Windows. You just open network neighborhood and will auto-discover whatever you have in the network. So the same way, NVMe targets have an option to advertise themselves on the network. It's just a shortcut. But the second URI is, if you know the host name, you can directly discover subsystems that are exported on the target. So going back to this file manager example, it will show up as icons, for example, all the exports, all the block devices. Or, of course, you can use your C API through GIO or a command line utilities. Or there's a Fuse daemon for POSIX access to GVFS resources. So this is only about discovery. And the next step, when you specify subsystem NQN, the GVFS backend will initiate connection. So it will appear as a namespace on your system, as a block device. And immediately, it gets scanned by UDEV for partitions. The existing GVFS eDisks to volume monitor will treat it as a local disk. So it will offer you to mount whatever is there. And there is no difference, essentially, between plugging a USB stick in your computer than connecting something over NVMe over TCP. So this is where the RFE stops. At this point, we are still discussing what's going to be happening next and what the other directory structure will look like. Maybe it will be just symlinks to mounted block devices or partitions on the namespace. Or it will just translate the URI transparently to your file. It doesn't matter. It will always go through local POSIX access. So this serves as an entry point for mounting a namespace, and it doesn't matter if you use it from GUI or using a POSIX access anywhere else. It might show up in /media or run media or something. So the point of this RFE is to just provide user interface for connecting and browsing the resources on our network. Technically, it will be backed by eDisks, where we have implemented almost fully-fledged NVMe initiator built on libNVMe. There is no difference in the dbus interfaces between fabrics and local SSDs, so it's already in place. It already works. I'm not sure if GNOME Disks has support for NVMe this way, but it's coming definitely. So there will be another way of managing your local NVMe over Fabrics connections. So that's all from me. Again, this is just an RFE. We will welcome your comments upstream. We will welcome your contributions. There is still a way to influence how this would look like. So feel free to reach to us, and hopefully it will come useful to somebody. Okay, thank you. Do we have time for questions? One question?
So NVMe is block level, right?
Yes.
So how do you get a path?
So the question was that this was a block device and how we get file system on it. Basically, once it appears as a namespace, as a block device in your system, you just use it as a local block device. It doesn't matter. You partition it through regular tools. There is no difference. It's all abstracted by the kernel. So really, no difference between local disks or USB flash sticks. There was a second question.
So maybe side related to your work, but what brings NVMe or TCP compared to iSCSI?
So the question was the difference or benefit between NVMe over TCP and iSCSI. So iSCSI is complicated. NVMe is much more clean specification. Well, it strives to be a lower latency and more performant. There is like no strong reason to ditch iSCSI for the moment. But we are trying to unify the access to NVMe over fabrics and enlighten the user base for the adoption. That's the most primary point. Okay, so we are out of time. I will be here. We have 20 minutes breaks, I think, so we can discuss further questions already. Okay, thank you.